All right, let's talk about something really cool in AI architecture. Now, the name is a bit of a mouthful, I'll give you that. Manifold-Constrained Hyper-Connections. But trust me, this is a huge deal. It might just be the secret ingredient we've been looking for to build truly massive, stable AI. So, let's break it down.
So why does building these giant AI models sometimes feel like you're building a house of cards? You keep stacking layers, making it bigger and more powerful, and then, suddenly, the whole thing just collapses. It's a huge problem. So what's the weak link here? What's going on under the hood that makes these amazing systems so fragile?
Well, it turns out the answer isn't about the engine, it's about the roads. The invisible highways that carry all the information through the model. And believe it or not, a recent breakthrough has basically given these highways a set of incredibly smart guardrails, and that changes everything.
Okay, so to really get what makes this so revolutionary, we need to rewind a little bit. Let's talk about the absolute bedrock of modern AI, the one thing that allowed us to build these incredibly deep networks to begin with.
So, for the past decade or so, the undisputed champion of deep learning has been something called the residual connection. The best way to think about it is like an express lane on a highway. It's a brilliant little trick that lets information just bypass a whole bunch of traffic or, computational layers, so it doesn't get lost or garbled along the way. Super simple, super effective.
Now, the magic of this express lane is something called identity mapping. It sounds technical, but it's a simple idea. It means the signal can get from point A to point B, way down the line, completely untouched. It's like perfect signal preservation. And that property, that clean, direct path, is the absolute foundation of stability when you're training these massive, massive models.
And just look at it. It's so elegant in its simplicity, right? The input just has this clean, straight shot through the network. This simple idea is what's powered so much of the AI boom. But what happens when you decide one express lane isn't enough? What happens when you try to build a super highway?
All right, so this is where things get really interesting and a little bit dangerous. Let's see what happened when researchers tried to put this thing on steroids to squeeze out even more power.
So, they came up with this new architecture called hyper-connections, or HC for short. And if our original connection was a single express lane, think of HC as a 10-lane superhighway. It's wider, it's faster, it's designed to handle way more information and boost performance. But there was one tiny little problem. They forgot to install any guardrails. And you can see the difference right away. That single, clean path is gone. Now we have this big, wide residual stream where all these complex connections are mixing the information up. It looks more powerful, for sure, but that complexity, well, it came with a very nasty surprise.
And that surprise was chaos, total instability. This hunt for more power had accidentally created a catastrophic flaw that only showed up when you really pushed the system to its limits.
So what went wrong? Well, it all comes back to that identity mapping property we talked about. By ripping out that simple express lane and putting in this big, messy superhighway, they'd accidentally destroyed the one thing that was keeping the whole system stable. That beautiful, clean signal flow, it was gone.
And here is the smoking gun. This chart shows the model's training progress. And you can see, everything's going along just fine, learning, getting better, and then bam, that huge spike. That's called a loss surge. It's basically the AI equivalent of the whole system just having a complete meltdown. Performance falls off a cliff, it's completely out of control.
So what was happening inside the network? Well, without those guardrails, the signals on that superhighway were going haywire. They were either just fizzling out and disappearing, or even worse, they were amplifying themselves over and over again until they completely exploded.
And this chart just puts it into perspective. It's measuring how much the signal is being amplified. And just look at that peak over 3,000. That means a signal was getting magnified by 3,000 times just by passing through the network. I mean, that's not just unstable, that is a guaranteed recipe for a complete and total system failure.
So what do? You've built this incredibly powerful superhighway, but it's dangerously unstable. Do you just tear it all down and start over? No, you get clever. You engineer some smart guardrails.
And this is where the hero of our story comes in, Manifold-Constrained Hyper-Connections. We'll call it mHC. The idea is brilliant. Keep the big, powerful superhighway, but add in those smart guardrails. And it does this using a cool mathematical concept called a manifold. You can just think of it as a set of rules that forces the information to flow smoothly and predictably, keeping everything under control.
And if you look at the architecture, at first glance it looks a lot like the old, unstable one.
But the key difference is inside that residual stream. Those connections are now mathematically constrained. It brilliantly brings back that core principle of signal conservation, that identity mapping. But you still get all the benefits of the wider, more powerful connections. It's really the best of both worlds.
So how does it actually work? Well, without getting too deep in the weeds, it's basically a three-step dance. First, the model figures out the connections it wants to make. Then, a very clever algorithm gently nudges those connections so they fit inside a strict set of rules. And the final result? A perfectly balanced matrix where the total amount of signal going in is the same as the total amount coming out. No more exploding signals, no more vanishing signals, just perfect, stable flow.
And this is what I love. You can literally see the difference. On the left, that's the connection matrix from the unstable model. It's a total mess, right? It's just chaotic. And on the right, that's the matrix with the mHC constraint. It's perfect. It's ordered. It's the visual definition of taking chaos and turning it into elegant, stable order.
Okay, so the theory is beautiful, the pictures are convincing, but the billion-dollar question is, does it actually work? Did these smart guardrails deliver in the real world? Let's check out the results.
And the answer is a huge, emphatic yes. I mean, look at this. The mHC model didn't just train without blowing up, it smashed the baseline across the board. And check out the reasoning benchmarks. A jump of more than 7 points on BBH? That's massive. It proves the model isn't just more stable, it's actually smarter.
But here's the kicker, and this might be the most impressive part. How much did all this extra stability and performance cost in terms of training time? Just 6.7%. That is an absolute bargain. For a tiny bit more compute, you fix a fundamental stability crisis and unlock a whole new level of performance. So, let's wrap this up. What have we learned? Basically, mHC is a game changer. It tames the wild instability of these more advanced connections. It delivers seriously better performance, especially on those really hard reasoning tasks. And it does all this without bogging down the training process. This isn't just a patch, it's a robust solution that's built to scale.
You know, this isn't just about fixing a bug. It's about opening up a whole new frontier for AI design. Now that we know we can build these more complex, more powerful architectures without them falling apart, it really makes you wonder, right? With this kind of stable foundation, what incredible new things are we going to be able to build next?